So first of all, thank you for the organizer for giving me the opportunity to present this work. So I'm going to present a new technique for the measurement of ultrashort laser pulses. So I expect that this is of your interest and you can apply it in the future. So the technique is called amplitude swing. And okay, so first, this is a new technique, and first of all, I'm going to give you the motivation to develop this technique and the basic for the measurement of ultrashort laser pulses. Then I'm going to present the new concept that we have applied for the amplitude swing technique, and I'm going to show you how it can encode the spectral phase of the pulse. That is what we are going to measure. I want to present an analytical model to understand what is happening and how it encodes the phase. The first simulations to test the technique and the reconstruction algorithm to retrieve the information of the pulse, and the first experimental demonstration. Okay? And finally, I'm going to present our last studies on this technique, in which we have studied the response for different parameters that can influence in this technique and how it can determine the retrieval of the pulse or not. And finally, the conclusions. So first, why are we interested in ultrafast lasers? This is because they have many different applications for characterization of sources, for metrology, particle acceleration, communications, nonlinear optics, nonlinear processes. And there is not only the applications, but we need in these applications to measure the pulse. And this is important because we need to understand what is happening and we need to optimize the applications. For this, the characterization of the pulse before or after the application is very important. There are many applications, as I have said before, and just to highlight here two biomedical applications that are very recent. Okay, when we are going to measure an ultrashort laser pulse, we need to keep in mind that they are in the femtosecond scale, so they are very short emissions of light, and because of this, they have a very large spectral bandwidth, and we need to determine the amplitude and phase of the pulse in the temporal domain or in the spectral domain. This is equivalent because they are related by the Fourier transform. And in our particular case, we are centered in applying it to titanium sapphire laser pulses with central wavelength around 800 nanometers. But this concept can be also applied to different spectral bandwidths and different spectral regions. Okay. So what is the amplitude swing concept? So now imagine that we have our pulse that we want to measure. We create a second replica of the pulse with a certain delay that we can control. And then what we are going to do is that we are going to vary the relative amplitude between these two replicas. So this is represented here in this picture. So this is the first replica that arrives before. The second replica arrives after. This is the temporal domain. And we can vary the relative amplitude. So first, we only have the first replica. It decreases the amplitude. And at the same time, the second replica, originally the amplitude is 0, and then we increase the amplitude. When we overlap these two replicas, the result is this. So first only one replica, last only the second replica, and in between there is the interference. And this interference is key to understand what is happening after. So we not only have here this linear process of overlapping two replicas, but we need to perform a nonlinear process, any nonlinear process. And in our case, we choose to perform second harmonic generation. So we are going to see here in this animation, in this movie, is that in the temporal domain, the fundamental has this expression, has this form. We are varying the relative amplitudes of the pulses, and we are seeing the overlap. And what we see in the bottom picture is that the second harmonic signal is varying the form when we are varying the relative amplitude of the pulses. Okay, so this particular example is for a pulse with linear chip with negative GDD, and what we are going now to compare is what happens if the phase of the pulse is different. So now if we have two pulses, different pulses, one with negative linear chirp and one with positive linear chirp, we are going to see in the bottom pictures what happens with the second harmonic. we see that we are varying again the relative amplitudes, and now the key is that this second harmonic signal is different from the negative pulse than for the positive pulse. So this means that we can distinguish the phase of the pulse if we measure this second harmonic signal. So we can take different snapshots of this animation, of this video, and what we see here is that in the left for the negative chirp, if we put at different positions of this amplitude balance, of this amplitude variation, we see that the interference in the temporal domain above, for example here, has a bluish wavelength, and also the second harmonic is going to have this bluish wavelength. And if the pulse has positive chirp, we are going to see the opposite. We have the same temporal profile of this interference, but the instantaneous wavelength, the spectral content is different, and then the second harmonic signal is different. So they are encoding the phase. So what is the important thing here? This is not only the concept, but also the experimental implementation. So the experimental implementation is very simple. What we are going to use is to create this amplitude variation is simply a multi-order wave plate with certain thickness, a birefringent plate that introduce an exact delay between the two replicas. Okay. What we can do is that if we start with input linear polarization, horizontal, okay, and if we rotate this multi-order wave plate, we're going to create two replicas of the pulse, the first replica and the second replica. Okay, we're rotating this plate, and then we are selecting these two replicas with a second linear polarizer. We choose it to be horizontal, and then if we are rotating this plate, we are creating these amplitude balances for different orientations of the multi-order wave plate. Okay? So now we have created the replicas, and we now need to perform the nonlinear process. So for this, we can focus onto a nonlinear crystal. If we have enough intensity, we don't need to focus, so the lens is optional. And in this nonlinear crystal, we generate second harmonic, okay? And after that, we need to filter it and to remove the remaining fundamental and to detect the second harmonic for different orientations of the plate. Okay. To understand what is happening, we did an analytical model. So we simulated the pulse in a simple case, assuming that it's a Gaussian pulse with a Gaussian spectrum, and that we only have a pure linear chirp with a pure GDD that we modelize with the B parameter. Okay, so this gamma parameter is the bandwidth of in the spectral domain, and we consider that the multi-order wave plate has this birefringence in the refractive index and this thickness T, and because of this difference of optical path, we are going to introduce the delay I said before. Okay. And then we simulate the effect of rotating the plate and selecting with the linear polarizer. So the final expression of the electric field in the fundamental domain, the overlap of these two replicas, is this one. And if we see, we have two replicas with a delay, and when we rotate the plate, they are balancing the relative amplitudes. Okay? We can perform all the calculations and obtain the expression of the second harmonic signal, this two-dimensional trace that depends on the frequency or wavelength and depends on the orientation of the plate, and we find this expression. Okay? What we are interested here is in measuring the dispersion. So we are interested in retrieving the V parameter. So we see that it's encoded in the terms that depends on the angle on this certain form. And we are going to see into more detail why the phase is encoded here. So step by step, the model I have said you, so we have this Gaussian pulse, these two replicas, and because of the plate, we have this superposition of these two replicas. Okay. Now, we square the signal to calculate the second harmonic in the temporal domain. So we have the second harmonic of the first replica, the second harmonic of the second replica, and the crossed sum of frequency of these two replicas. Okay. And then we can move to the spectral domain. So we have the three same terms. And if we calculate the spectrum of this signal, we have the same expression than before. And we see that the two terms that are encoded in the phase are the interference between the second harmonic of the first replica and the cross term, and the second harmonic of the second replica at the cross-term. So this interference between these second harmonic signals is key to encode the phase. With this analytical model, we calculate the trace as a function of the spectrum that we are detecting and as a function of the orientation of the plate. And we see that for different linear dispersion, linear chirps, we obtain different traces that corresponds that we are again encoding the trace. So from this model, we can understand more things, and we see that the terms that are encoded in the phase, first, they have this negative exponential, and because of this, we see that if the delay between the two replicas is very long, then this term is going to be 0, so this is not going to encode the phase anymore. And in the opposite way, if the delay is very short, the term that encodes the phase, the argument of the cosine is going to disappear. So we need to keep a delay that is not very long, not very short. And the reference for us is the Fourier limit of the pulse. Okay, so we need to be relatively close, 2 or 3 times above or below the Fourier limit of the pulse. Okay. So now we are not only limited to measure linear chills, we can measure any phase, any spectral phase. And for this, we do now a numerical model, a general model, in which we have any arbitrary amplitude and phase of the pulse. Okay. And we can directly measure the amplitude of the pulse from the spectrum. And we use amplitude swing to retrieve the spectral phase and to retrieve the characterization. Okay. So we again consider the multi-order wave plate, but now it's a general wave plate. If we know the material, we know the thickness, we can calculate the dispersion of the slow and the fast axis, and we can compute it here. And then we simulate the second harmonic trace. So for this, we Fourier transform to the temporal domain, we square to calculate the second harmonic, and we go back to the spectral domain and we calculate the spectrum. So this is the general expression. And now we have this expression, and from this expression, we need to retrieve the information of the pulse, which is not trivial. This is not a direct inversion. For this, there are different approaches. The important thing is that with our spectral phase is not a single parameter, but this is a function that we need to optimize. And for this, we need to do a parametrization. We can do any Taylor or Fourier series, discretization of the function or the derivative. And in our particular case, we do a first retrieval approximation of the Taylor expansion, and then we obtain an arbitrary phase with the discretization of the derivative. Okay? The algorithm that we need to use to obtain this unknown function, because we have multiple unknowns, we can use different algorithms. We can use nonlinear optimization algorithms. For example, these two. This one highlighted here is that the one that I am using. And we can also use genetical algorithms or artificial intelligence. But the important thing is that all of them are going to calculate a theoretical trace, are going to compare it to the experimental one, and from this comparison are going to obtain the spectral phase of the pulse. This kind of algorithms are iterative, so we know this expression, this theoretical expression of the phase, of the trace, sorry. So we start with an arbitrary case phase, for example, Fourier limit or any one. We calculate the electric field of the pulse. We calculate the theoretical expression for the trace, for the amplitude swing trace, and we compare it to the experimental one. From this comparison, we obtain a merit function, for example, the root mean square. And from this comparison, we know what variations we need to do in the phase to be closer to the solution. So we obtain a new spectral phase, we calculate the electric field, calculate the trace, and do this in an iteration. When the merit function or the error is very low, down, below a threshold that we establish, then we have the solution and we have the spectral phase. Okay? So for the simulations as I showed before, we have done the reconstructions using this algorithm. And for example, we see here for different GDDs, the simulated trace above and the reconstructed trace. So we see that we can reconstruct the trace and we can obtain the phase. And also we can see here in the spectral domain above and in the temporal domain below for these different GDD values, how we can retrieve the temporal intensity, the temporal phase, and the spectral phase. Okay. We did a second simulation now with third order dispersion. And what we see here is that, again, for different third order dispersion values, we have different traces. We can reconstruct them, and we compare our reconstruction with the original simulation. So we obtain a very good agreement. So what happens if we have a phase that is different? It's not a pure GDD or TOD. So for example, if we have this oscillatory phase, which is very low in radians, it is kept below 2 radians oscillation, we see that we can retrieve the generated trace, okay? And the comparison between the spectral phase retrieved and the simulated one and the temporal intensity and phase is also good. So we can retrieve, in principle, arbitrary phases. So now the simulations have shown that the technique is working. So what happens with the experiments? And in the experiments, we are using a titanium sapphire CPA laser with 10 nanometers spectral bandwidth, 84 femtosecond Fourier limit. And what we are going to measure is the pulse for different positions of the compressor. Okay. So when we vary the compressor, we are compensating the second order dispersion, the GDD, but we cannot compensate perfectly the third order dispersion. So in the best compression case, we have a remaining positive third order dispersion. Okay. We use a plate with introducing 100 femtoseconds. This is a quartz plate, and with this first phase retardation for the center wavelength. To check our results, now we don't have simulations. This is an experiment, so we are going to compare with a well-established technique, that is the self-calibrating the scan. And in this technique, what we do is that we measure the grating compressor position, the distance between the gratings, and we compress the pulse below or after the compression. So we introduce negative or positive GDD. And while we are doing this, we measure the second harmonic signal. So we have the second harmonic, and we have negative dispersion, zero dispersion, and positive dispersion. Okay, and from this second harmonic signal, we can reconstruct it with a similar algorithm, and we obtain the pulse for different positions of the compressor. So we are going to measure the pulse at position A, B, C, and D. Position A has mainly negative dispersion. Position B has around zero GDD with the third order dispersion remaining. And position C and D has increasing positive GDD. So this is, in the first case, in the position A, the experimental trace with the amplitude swing. This is the reconstructed with the algorithm, and we compare the spectral phases with the known technique, with the D-scan, and with the new technique, with the amplitude swing. So we obtain that the phases are very similar. We calculate the second and third order dispersion terms, coefficients, and also we can calculate the temporal intensity and compare them, so we obtain very similar reconstructions. We can do the same for position B, C, and D. Okay, and in all of them, what we are seeing is that the comparison between the amplitude swing and the D-scan reconstructions are very good, and also in the temporal intensities, we have good comparisons. Okay. In our last study with this technique, we have simulated the effect of different parameters. So for example, what happens if we have a trace for a combination of GDD and TOD, and we add noise to this trace, simulating experimental noise. So we have here different levels of noise added to the traces, and we have in the different columns the reconstructions. What we see is that for small values of the noise, we retrieve the trace correctly despite of this noise, and we retrieve the pulse correctly, and up to 5% the retrieval is rather good, is relatively good. Also, we have checked what happens if with the multi-order waveplate is half waveplate or quarter waveplate, complete waveplate, or intermediate cases, and we see that for these different cases, the trace is of course different, but if we know these phase retardations, we can retrieve the trace and we can retrieve correctly the pulse. Also, we have checked what limitations are with the delay with respect to the Fourier limit of the pulse, and we have checked that we can keep 2 or 3 times above or below the Fourier limit of the pulse, and we still can retrieve the pulse correctly. So we have rather versatility. And also we have checked what happens if the trace, the second harmonic trace, is not complete. So there is missing information. So for example, if there are traces in which we don't have information, and we see that up to a limit, we can still retrieve the pulse information for this spectral clipping. Okay. Something that is happening when we are measuring ultrashort pulses is that they have a large spectral bandwidth, and because the phase matching, we cannot convert all this bandwidth with a flat response. So we have calculated the frequency marginal of the trace. We have calculated it in a theoretical way, which is included in this article, in this paper. And we can use this marginal to calibrate the trace. Okay, so actually what we are going to do inside our retrieval algorithm, we are going to calculate this marginal. We are going to compare to the experimental one. And from this comparison, we are not going to retrieve only the phase, but also we are going to retrieve the second harmonic response of the spectral conversion, the second harmonic conversion, and also of the spectrometer. So these are some simulations in which we retrieve this, we simulate this non-flat second harmonic response, which narrower response in the right panel, and we still can retrieve the pulse, and also we retrieve this response of the second harmonic, which can be due to the phase matching bandwidth of the second harmonic crystal. And this is very important. For example, if we go to few cycle pulses, and we have here a simulation in which we have the combination of these of several of these parameters, we have the ideal trace simulated, and what happens is we have some spectral clipping in both sides of the signal. We add noise, we add a delay different from the Fourier limit, and what we see is that still we can retrieve the trace, and not only the trace in which we have signal, but we also retrieve the complete trace, and we retrieve a pulse that is equal to the simulated pulse. So this is a very good result. And we did some experiments to check what happens if we have these different delays and further different retardations of the plates. So we applied it to 3 different pulses. So we have a pulse that is always the same spectrum with 60 femtosecond Fourier limit. And in the first 3 cases, this is with the GDD compensated. Then we have 3 cases with the negative GDD and 3 measurements of the pulse, positive GDD, and 3 cases with the pulse of negative GDD. So we measured it with these 3 different measurements, with these 3 different plates, and we see that the 3 retrievals are the same for the first case. The 3 different retrievals for the second case are also similar, and these 3 retrievals are the same, despite of using traces introducing different delays from 20 femtosecond to 95 femtosecond. The final result I'm going to present you is what happens if we measure the pulse with this non-flat second harmonic response, and we are going to compare the response of a BBO crystal of 20 micron with flat response and a thicker crystal with 300 micron with a non-flat response. So we have this measured trace, and what we find here is that if we calibrate the second harmonic response with the retrieval algorithm, we retrieve this orange curve here that is the same here that we can obtain from the calibration of the crystal. So we retrieve the second harmonic response, and we retrieve the spectral phase of the pulse that is similar than with the previous measurements. Okay. So to conclude, the amplitude swing technique is a new concept that has a very compact setup. It's very simple. It has very few elements. There are no interferometers. In despite of having 2 replicas, the interferometer is built with the multi-ordered wave plate, so its mill is built in bulk, so it's very stable and it's very easy to be integrated in different systems. And because of these parameters flexibility that I have shown before, it's very versatile. It can be applied to pulses with different bandwidths and in different spectral regions and with different durations. And also it's very robust against noise, spectral clipping, or non-flat response that is present sometimes in this kind of experiments. So we expect that it has many different applications in different fields, as spectroscopy, microscopy, particle acceleration, and so on. So that's all of my part. So thanks for your attention.
Yeah, thank you so much, Professor. That was a very enlightening speech. So we'll wait for some time. If anyone have any question or comment, you can please go ahead and ask Professor Benjamín.
I have one question, Dr. Benjamín.
Yeah.
What is the cut of your BBO crystal first?
What is?
What is the cut? It is a second harmonic experiment, so there must be some crystal cut.
Crystal cut. The cut, the angle of the optical axis. Do you mean? Or?
I mean, for phase matching is concerned, you need some particular cut, second harmonic cut or third.
Yeah.
So what is the angle? What is the angle for your experiment?
Yeah, so we use crystals that are cut for efficient generation of second harmonic at 800 nanometers. So the angle of the optical axis is 29.2 or something like that, around that value. So if you are going to use the same crystal for a different spectral region, you can rotate it to optimize. We do it, for example, if the pulse is at 600 nanometers, or you can use a different cut.
I'm interested to know another thing. Once you go for the vertical rotation.
Sorry?
Vertical rotation.
Vertical rotation.
So how your, generation was changing with vertical rotation?
I'm not understanding, sorry. Some noise.
I'm asking, when you rotate crystal vertically, because you put a crystal, right? And you are rotating.
Yeah, no, so we rotate it in this direction.
Horizontal direction, not in vertical direction.
Yeah, no, not in vertical. No, in this direction. Okay. So this is the beam. So the rotation is in this direction. So if you are not very far from 800 nanometers, you can rotate it and you can still have efficient second harmonic generation. So we have rise up to the fundamental beam around 1.5 micron wavelength, and we still have some efficient second harmonic generation that we can use to characterize these pulses.
Okay. Okay. Thank you.